All right, thank you. So yeah, I'm going to talk about various topics about random number generation and extraction. I'll most likely go more in breadth than in depth, but please ask questions, and if something is needed, I'll try to go to the board. Okay, so some introduction to the area. So randomness is needed everywhere, so all kinds of applications to approximation algorithms, distributed computing, property testing, counting problems, symmetry breaking, game theory, of course, like Nash equilibrium, and so on. And last and not the least, it's also very important in cryptography, as we know. So what are some of the applications of randomness in cryptography? Most important probably is that secret keys have to be random, otherwise it's not clear what secret means. For privacy, encryption, secret sharing, zero knowledge, for every use you need to kind of randomize things so that if you encrypt the same message twice, you get different results. Preventing replay attacks for various unpredictability, communication complexity applications to reduce communication using randomness, anonymity, of course, differential privacy, noise, and so on. And also even just efficiency, like primality testing, for example, the best known, even though there is a deterministic primality testing algorithm, the most efficient ones, the ones that are used are randomized. So definitely we need randomness everywhere. And even, I don't know much about it, but I heard that in blockchain cryptocurrencies, they also use randomness in things like snarks and so on, Byzantine agreement. So anyway, bad randomness leads to attacks. This is the last cartoon that I'm going to use in the talks, and then we'll turn serious. So this is like a very incomplete list of attacks. And the common thing about those attacks, I'm not going to go with them. So there are some famous ones, this mining P's and Q's, where people found like essentially badly generated randomness for SA keys and so on. Maybe the common feature of all those things that it's not maybe easy to attack cryptography or to break randomness and to break random number generators, but when they fail kind of spectacularly. So it's, as it says, attacks that result from RNG failure are spectacular, so we better not have those attacks, right, because that's pretty bad. All right, so the question is, where do we get this randomness? So we want to look a little bit under the hood to see where we get randomness in computers of applications to cryptography. And the answer is pseudo-random number generators, right? So every kind of operating system, so whatever device or something, if you want to use crypto, you need to have some random number generator. So what is a random number generator? Maybe here this red button is not as well known as the United States. So in the United States, there is a store called Staples. So that's like this red button. It says like, that's easy. So that's like a famous thing. It's like when they need something, you just press a button and it happens. So for PRNG, this is what it looks from the user. It's one of those Staples button. You just press it and a random number comes up. You press it again, another random number comes up. So from the user perspective, it's a very nice interface. You just press a button and you get a fresh, independent random number, and you keep doing it. And of course, we need to want to look under the hood and see who builds this red button, right? So how does the Staples create this red button? And in reality, what happens is there are more choices here. There are physical random number generators like Intel builds them and so on, but the most common ones, at least currently, are the ones that look at this thing is called entropy sources. They look at things which are believed to be unpredictable. Some people use like quantum effects and so on, but something which is believed to have entropy, they're called entropy sources. The most common one will come up later is timing of interrupts. There are all kinds of interrupts happen on the computer, and it is believed that nobody knows. There are so many like random things that happen that the actual like nanoseconds of these interrupts nobody can predict. But the common thing about them, even though they have entropy, so they're somewhat unpredictable, they're not perfectly random. They're not uniform, not independent, not fresh, and in some cases even somewhat adversarial. For example, the attacker might be able to, if it's like some kind of shared virtual machine or something that can cause interrupts and even partially control some of those interrupts. So you can even think from our modeling that they could be adversarial. So I want to, before I tell you, we'll spend 3 hours kind of building those things kind of very slowly and so on. So I want to take a little bit a bigger outlook. Okay, so this is characters from Lord of the Rings. So if you look at various cryptographic primitives, like block ciphers, authenticated encryption, digital signatures, hash functions, recently post-quantum competitions, they, all those things maybe started somewhat immature, but with time became more and more mature. For example, all of them have some standards, some competitions. People chose winners of these competitions. And more we get to the point where people don't just, if you need a block cipher, you're not going to say, okay, let me just, I don't know, design a block cipher. Right, you're going to probably use AES or something like that. Even though there are exceptions, people still design like weird things, and people like Itai break them. But more or less, things get to the state of being more and more mature, that people understand they don't need to design their own cryptography. So in comparison, this is kind of the state maybe of random number generation. So this is Golem. I think so. There is, don't get me wrong, there are some standards. So, for example, in the United States, there is this NIST, National Institute of Standard of Technology. It has a standard SP890A. Even the name is kind of bizarre. So it has some recommendations on how to build random number generators, but it's like in comparison to the other ones, I had some backup slides which I decided to erase, so I'll just say, in comparison to these more established standards, I would say it's pretty much very, very ad hoc. There was a Eurocrypt paper a few years ago that even sent as a standard. It actually wasn't precise. There were some things which, right, in standard, it has to be like precise, right? Everything has to be unique and ambiguous, but there were some ambiguities about it. It led to some attacks. There was also a fiasco with some, one of those things in the early version of the standard was this NIST DBRG thing, which, you know, there was like a big scandal about it. So it was believed to have a backdoor, and then it was removed. So basically, the upshot is that this is a pretty mature field. Okay, so in comparison to other things, so what we'll try to do, and even though I come from a more theory background, so our hope is to at least get it from Golem to Smeagol. That's like the same kind of character, but in a more less primitive form. So hopefully we are kind of here. But my point is, and I don't know how realistic this point, in principle, random number generator, it's basically, I mean, yeah, if you look under the hood, there is some adversarial attack, but this is a really simple interface. So this is just you press a button, you get a random number. It's not like encryption, decryption. There is a sender and recipient, or like multiple parties doing stuff. It's literally just one party pressing a button. So in principle, there is no reason why this shouldn't be the most powerful of them all. I don't know who this guy is, but, you know, pretty powerful guy. So the philosophy is I'm actually hoping that I'll try to convince you during this tutorial that there are a lot of interesting and cool questions, both from a theoretical side and applied side. And in principle, there is no reason why this shouldn't be as mature as some of those other fields. Anyway, so this was my introduction with pictures. So let's next ask the question before we move to theory. So I will start with kind of real-world crypto, if you wish. Well, okay, so we don't have the standards and so how do people use, right? So we have like our you know, TLS connections and things like that, some whose keys get generated and things like that. So people, despite being in an immature state, people still solve it. So if you look at popular operating system RNGs, they're not built according to any standard. And basically the way they're built, there is like a bunch of hackers in each of those groups. Like Linux has their own hackers, Windows, and they just do something and hopefully don't screw up. So one thing that will come up later, there's some good ones, the ones that basically conversion people are relatively comfortable using, use cryptographic hash functions, but, you know, we'll see anyway. So let's look a little bit of case studies. So we'll go a little bit to Linux, starting with Linux and then with Windows and Apple. So def random very soon is going to change, finally, after many years. But def random and def urandom, for those you know, it's basically security by obscurity. It's very complex, so I don't even know, but some hacker just said, okay, let's do something kind of crazy that nobody else is going to break. Just, I don't know, no theory, just kind of warm and fuzzy feelings. There is no intuition or security proof. It's just, I don't know, like some lines of like crazy shifts and, I don't know, things. It uses a hash function, but not in the place where you think it should use a hash function. And indeed, in one of my early papers on the subject, I did the theoretical part, but I teamed up with people who did more applied stuff at CCS-13. What we looked at Linux, we looked at this 800 codes, and I designed kind of a model, what it would mean to be secure and so on, and we tried to design something, but according to the models that we designed, we looked at Linux, and it was pretty easy to reverse engineer, even though it looks like a mess, but if you have a precise model in mind, it was pretty easy to reverse engineer and break it, at least in theory. According to our specification, it was very easy to show that it doesn't accumulate entropy. So the attacks are theoretical. I cannot really control the interrupts to the levels of our attacks. So it's not like we, broke in the real in the world, but at least theoretically it's completely broken. It's just there is basically no cryptographic security there. And there is more stuff is happening. But if you fast forward 9 years, I would say a lot has changed. So this is an email that I got at the beginning of this year. So Nadia is Nadia Hedinger, who introduced me, because I've been talking to people. It's like, yeah, we've been doing a lot of cool things. Do you know anybody who is actually in charge on these things? Can they use some of our things? So Jason Donenfeld, he is actually in charge of Linux RNG, and I met him at Real World Crypt, I think, before the pandemic. Nadia introduced us. And he said, so he wrestled eventually control of Linux RNG. I don't want to describe the process, blah, blah, blah. But then he writes basically 5 pages of what he's currently thinking about it, very, very detailed, and he concludes, so this is approximately my thinking is in the moment, but I'm all ears of any suggestions you might have, or if you'd like to try to come up something new together. My goal, so this is an important thing, my goal for this project is to have every component as rigorously proved as possible. So I think it's a great progress from this security by obscurity, at least. So right now people finally realize, okay, this is too important to get it wrong, so let's try to get it right. So, and indeed, this is just a little bit more. Then this is part of both the emails and the blog post that he puts on some Linux forums about his thoughts. But in particular, we'll go all these papers we're going to cover, but I actually feel almost flattered. So all the references that he puts to my papers, so papers written by our group, which was great. So trying to kind of take various things from the various papers from starting CCS-13, Crypto 19, Crypto 25, last year Crypto, and so on. So basically in the design, and I'm still working with him right now. So we are not done, but I'm hoping that we'll get, the next version of the Linux RNG will be much more theoretically sound than the previous one. All right, so and hopefully, if all goes well, I'll mention a little bit about most of these papers, so at least give you some kind of background of what we've been doing here. Very briefly, going to Windows and Apple. So they're actually more mature already. Apple uses, even though they're also in the process of changing it, so they're using something called Yarrow. Windows is using something called Fortuna, and those are pretty good designs. So when I looked at them, I actually, specifically worked with Apple to kind of help them find any weaknesses and so on. I couldn't really, unlike Linux, I couldn't find too many theoretical weaknesses. And in fact, they seem to be working well. And in fact, Fortuna did something that we'll talk at the very end of the tutorial, maybe 2.5 hours from now. Well, but basically, the last things I'm going to talk, is actually look at a very cool problem called premature next. I'll define what it is towards the end. So it's pretty cool design. So in comparison to Linux. And so what we did, we also analyzed this Fortuna in Crypto 14, and now in the upcoming ITC paper. So again, that I'll talk about the very end of this tutorial. And also something called super fast entropy accumulation, which is present in both of those designs, also analyzed in our recent papers. So basically, the reason I'm putting these things, so those were somewhat well-designed RNGs. I don't want to say by coincidence. I'm sure engineers had some designs, but they were pretty cool inspirations from us. We looked at something which we seemed to work well, and then we applied some theoretical tools to analyze it and slightly improve them. For example, we slightly optimized something in Fortuna that Niels Ferguson actually changed a little bit some parameters based on our analysis. So I think it's fair to say that even though here we started from practice and applied theoretical work, that there was a little bit of feedback backwards as well. So, all right, so the rest of it I'm going to, hopefully I motivated the problem, even though at some point we'll talk about like Fourier analysis and things like that. Hopefully I motivated the fact that these are really cool problems, of great importance in practice, and they are ripe to applying theory. All right, so let's try to apply the theory. So back to our picture. So it's hard to put those buttons in lattice, so we're going to just kind of collapse it into more mathematical notation. So first we're going to look at the simpler problem. Actually, for the whole first tutorial, before we switch to pseudorandom generators, we'll look at the simpler problem, which is just a problem of randomness extraction, but arguably it's one of the hardest problems to solve before we want to build the full pseudorandom number generator. So randomness extractor is just, so basically instead of producing the sequence of, it's just like one press of a button, right? So we don't want to press button many times, we just want to press button once. So let's abstract it further. So our goal is to take those messy entropy sources and apply deterministic function and to produce a string which nobody can, which no distinguisher, no attacker can tell from truly random string. Okay, so this is our goal. So we'll call this thing X. It's easier to type than to draw those kind of pictures. The deterministic function we'll call X, and the output we'll call Y. So basically, we want to design this function that take X produces Y. And the goal of the attacker is to distinguish Y from truly uniform. Okay, so this is a classical problem. Of course, the key is in details. What are the assumptions about X? How do we model entropy sources? So that's going to be our thing. And the gold standard here in this field would be to use something called mean entropy. I'll define it a little bit later more formally. But this is the right notion of entropy for randomness extraction. And so the gold standard would be that as long as our source, the only thing we want to assume is that it has entropy, measured in this mean entropy. And the moment the source has entropy, the output is uniform. Okay? So that would be our gold standard. Unfortunately, at least in this generality, we'll see exactly the boundary of what is possible and impossible soon. But in this level of generality, you cannot even extract one bit, provided gamma is not, unless the source is already full entropy. So, and this is kind of a trivial example. So take any function, extract. Someone says, oh, here is my extraction. It takes like this source and outputs one bit, maybe applies SHA-2 or whatever, something crazy, and does it. So here is my source. It's going to be uniform from the larger preimage. So without loss generalities, there are more zeros than ones. There are more inputs that map to zeros than one, or greater or equal. So you just make the source uniform on all the preimages of zero. It has almost full entropy. It has like, whatever, n minus 1 bits of entropy where n is the length of the source, and yet the output is fixed to 0. Right, so this is a little bit artificial, obviously, but we have to deal with it, right? So technically, there is an impossibility result. And actually, I'm going to take a detour from pseudorandom generators just because I love theoretical. So we'll start with like folk stock domain, like super theoretical papers that have nothing to do with reality, but kind of to build essentially from deep theory to practice. So let me take a little bit of a detour. The one question that I want to ask kind of conceptually, despite this impossibility, we said, okay, you know what? The golden standard for randomness extraction is impossible. I cannot like just extract from entropy alone. But who tells you that you need to extract for cryptography? Maybe I can do encryption without extraction, right? Or digital signatures or something like that. So this was like, so the first question we'll ask, can encryption, I'll focus on encryption because that's kind of the prototypical application. Let's say, can encryption be based on entropy alone? And there is an early paper of Benny Pincus, again, a super applied guy who does all this cool multi-party computation things and so on. But in his master thesis, that's actually how he started in cryptography. He had a paper at Crypto 91, which showed that no. And I'll give you this proof. I mean, I'll give you something more general in 2 slides from now. And what we showed, this was one of my early papers when I started to get interested in the field. What we showed is we significantly strengthened this paper of McInnes and Pincus in several papers at Fox 2004 and Crypto 15, that even if you're willing to make computational assumptions, you can assume whatever you want computationally, in some sense, in this level of generality, entropy alone is not enough to build, let's say, encryption. And so roughly speaking, the format of this kind of counterexample is that for any scheme, no matter what computational assumptions you make, for any scheme, there is some very high entropy source which efficiently defeats it. So the source would be even efficiently sampleable and so on. So at this level, I want to keep it high level without getting into detail, just to tell you the flavor of the results. So for any scheme, there is a high entropy source that will defeat the scheme. So you cannot have a scheme which is universally works for all high entropy sources, and even like pretty low entropy, pretty high, sorry. And it even extends not just to encryption, but to basically anything privacy related, like zero knowledge, commitment, and things like that. And then then I asked even a more ambitious question. So yeah, there was a question.
Before we go to the more ambitious question, so what exactly means, like, I'm just trying to understand what you mean informally defeating the encryption scheme. So you basically take an attack model. The entropy source is adversarial, like.
That's a good question. Yeah, it's adversarial. Yeah, so basically the flavor. I'm going to give you a negative thing for a more ambitious question on the next slide. But the flavor of these results is that the game is you. So here, to answer this question positively, it would be you want to design a single scheme and to have some kind of proof, possibly under computational assumptions like RSA or whatever you want to assume, that this scheme is secure, will be a good encryption scheme, even if the random source to generate the key comes from any high entropy distribution, right? So that will be the claim. And then in this negative result, we say, like, take any scheme, we'll show you, a high entropy source. We'll even, you'll have like relatively short description and so on. I'll give you a high entropy source which defeats the scheme, right? So you cannot have like a single scheme which simultaneously defeats all high entropy sources. That will be the flavor. But I'm going to show something for question 2, and hopefully it will be clear. But please ask me like 2 slides from now if hopefully you'll get the flavor of these results in a second.
Thank you.
But yeah, it's a good question. Yeah, I'm being informal here. So in fact, unlike ETA, I'll try to keep a lot of things with like pictures and a few things, 1 or 2 things. I'll go in depth, but if you're interested, ask me. We can go to the whiteboard and things like that. So here we asked even more. So this was like super negative, and then we asked an even more negative kind of view of the world. We asked the following question: okay, fine. Entropy alone is not enough, but entropy. So for example, entropy is not enough for both encryption and extraction. But even more ambitiously, is it true that encryption inherently requires perfect randomness? So basically, in order to do cryptography, we inherently need perfect randomness. What does it mean? And of course, if the source is like deterministically extractable, so formally it means, does it mean that if you have a source of entropy source for which you can do encryption, meaning like a family of distributions, and there is a single scheme that works for any distribution of this family, then this family is deterministically extractable, right? So there will be like a very negative result. It sounds like as a positive question, but that's like a very negative result. It means that really, in some sense, true randomness is inherent to do cryptography. And initially I had like, that was like one of my early papers in 2002 with Joel Spencer. That's the paper that gave me R-number 2, but that's not why we wrote it. So we kind of have some artificial source separating 1-bit encryption from extraction. So I gave you like a family of distributions, which is not deterministically extractable, but from which I can build a 1-bit encryption scheme, a symmetric 1-bit encryption scheme. So it gave us kind of hope. But then unfortunately, when I revisited this question with my former student Carl Bosley in 2007, unfortunately, we kind of showed that was like a little bit of a fluke. It's just a parameter choice. And unfortunately, the negative view of the world is indeed true. We showed that encryption, the moment if you have an n-bit key, right? Normally, let's say if the n-bit key is truly random, you can do one-time pad. You can take an n-bit key and encrypt n-bit message, right? And Shannon low bound, of course, says you cannot do better, but from our perspective, it's not bad, right? From n bits, you encrypt from n-bit secret key, you encrypt n-bit message. But here we showed that if you have an n-bit key, and a family distribution over n-bit keys, which allows you to encrypt even log n-bit message, that's just like a tiny kind of message, then from that family, you can deterministically extract a bit. So it's not quantitatively 1-to-1, and more generally, if you have an encryption scheme allowing you to encrypt like basically k bits, you can extract k minus log n bits. So up to this kind of additive log n, unfortunately, randomness, extractable randomness is inherent, and I'll give you even this proof. It's one of my favorite results. I just realized I basically never talked about it, and I really like it, so I'm going to spend a slide before we go. So it's a little bit of a detour, but hopefully you'll enjoy it. I try to fit this whole proof into one slide. So let's see. let's see why encryption implies extraction. Hopefully we'll learn. And one cool thing about it, we're going to use this Michael Jordan citation, but in reverse. So Michael Jordan says, always turn a negative situation into a positive situation. Here we're going to do the other way around. We're going to take a positive situation into a negative situation, okay? So, right, so what is a positive result? So I'm going to take a positive result about randomness extraction. I'll turn about, into a negative result about randomness extraction. So this is a positive result. It's a cool result. I actually, originated in Travis and Vadan, but I proved kind of a refinement of it in my thesis many years ago, before most of you were academically born, probably. So the positive result, which I'm not going to prove, but it has a cute proof, is the following: that if you have a family of distributions, and the family is exponentially large, but only singly exponentially large. So if you have a family of 2 to the n distributions, where each distribution in this family has enough entropy, it has entropy gamma, then you can deterministically extract gamma minus log n bits from this family. So basically, if you have one distribution, some kind of bin packing techniques or whatever, it's easy to see that from any distribution which has entropy, if you know exactly the distribution, it's very easy to convert it, like by some kind of bin packing, to convert it to uniform. And this result shows that you can simultaneously do it, even simultaneously for up to exponentially many distributions, 2 to the n distributions. And there is some loss of log n that explains why my paper with Joel Spencer had this gap of log n. But anyway, so this is a positive result. It's very cool. But I'll just take it as a given. Happy to tell you more details about it. All right, so this is a positive result of randomness extraction. So now let's get our negative result. So what is our negative result? I say, okay, assume you have, assume there is an encryption. It takes a key and the message. And this encryption allows me to encrypt gamma bit messages with n bit key, right? I want to argue that I can, so what does it mean? It means that assume the scheme is secure for some distribution family k. It could be triply exponential or maybe infinitely many distributions. I'm not saying anything about how many distributions. I said, listen, there's some family of distributions on the key that somehow this encryption is secure for every distribution in this family, right? So this is kind of my, my assumption. So I need to build an extractor. I want to say that I can deterministically extract from this distribution family, right? Okay, so one thing I will say, rather than extracting from the key itself, first I'm going to apply deterministic function. I'm going to encrypt a message 0 under the key. So I'll get the ciphertext, and I'm going to extract from this ciphertext. I'm just restricting my hands to the form of the extractor. So I will always first produce the ciphertext, and then I'll extract from this ciphertext, right? So this is a family S prime that I'm going to extract from. So now I'm going to create, define, so pay attention to the color. So this is what I want to extract, like this family S prime. I'm going to define a different family, capital F. So the capital F will be the following family. It will have 2 to the n distributions, 1 for each key. And the distribution is going to be encryption under a fixed key of uniform message. So I'm taking a fixed key and I'm encrypting a uniform message. Okay? So this is my family F. And now you should do some kind of pattern matching with the colors and so on. I claim that this family F satisfies my positive result. So let's see where it satisfies it. Let's see. Yeah, it satisfies positive result. Why? Well, it has 2 to the n distributions because the key is n bit long. So it has exactly 2 to the n distribution. So that's good. And each distribution, because encryption is decryptable, I mean, the result generalizes to some decryption errors, but I'll just state it like without decryption errors. For every key, if I encrypt different messages, I better get different ciphertext, otherwise I cannot decrypt it back. So it means that all those things, this 2 to the gamma messages all go to different ciphertext. That translates to exactly that, under definition of mean entropy, it means that every distribution here will have gamma bits of mean entropy. So I can apply positive result, and now I know that there exists a deterministic extractor. Okay. Of course, the elephant in the room is, well, we want to extract from this, and we know how to extract from this. So, but we haven't used the security of encryption. So somewhere we have to use the security of encryption, and I claim that this follows from the security of encryption. So namely, security of encryption says that encryption of a fixed message 0 under any distribution capital K from my family should look indistinguishable from encryption of uniform message, right? That's what security of encryption tell me with some whatever small laws. And now I can basically give the key for free for the attacker. Every distribution of this form, where capital K is a distribution, is a mixture with some weights of these distributions from my family F, encryption under fixed key of uniform message, right? So basically, any distributions that, so the distributions that I want to extract is statistically close to basically a mixture of distributions from which I can extract. And it's easy to see the extraction has this convexity that basically if I can extract from deterministically from this, from like 15 distributions, then the same extractor works for any convex combination. So that's the end of the proof. Sorry, it's like, yeah, I guess I'm going slower than I wanted, but I mean, I like this result, so it's a little bit of a detour, but I hope, I hope you enjoyed it. So, but yeah, anyway, so this was the end of my detour. So now the question that we're going to spend the rest of the tutorial is how to get this workarounds again, is this impossibility, and we're going back to encryption, to extraction. Okay, basically I said extraction is essential for cryptography, so let's see how we can do extraction. So there will be several workarounds, and we will see the cool thing about them that all of them basically are going to be used in different aspects of modern RNG design. So the RNGs that, for example, like Fortune and so on, to some extent, at least our modeling of the analysis will use all of those things in different places. But we'll get to it at the end of the second hour. For now, let's just look at it one by one. So what I'm going to spend this hour is on the first workaround, which looks a little bit ridiculous and not really useful, but we'll see it's useful and it led to a beautiful theory, is the ability to do seeded extraction. So what is a seeded extractor? A seeded extractor is, so normal extractor just takes a secret X and outputs the extracted key. Sorry, I call it Y, but I'm going to switch it to R, at least temporarily. Sorry about it, I forgot. But here we'll assume that there exists a second input to the extractor, which is a random seed S, which is public. So, and the security, you're saying, well, if I have a random seed S, what's the point? The point is that the seed S, you should think about it as a public thing. It kind of helps me to extract from X. So I'm really extracting from X. So even the joint distribution of my extracted output and the seed looks like uniform. And here, we're talking about statistical security. So even computationally unbounded attacker cannot tell them apart. And the canonical thing, the canonical application of this seeded extractor is think about the key derivation function. So, somebody like Ward Hart, and maybe we have a public seed S that is like known to everybody, but now I have my secret thing like biometric or Diffie-Hellman whatever element or something like that, and I want to extract my secret key. And a key property, a key measure of efficiency here. So previously we said deterministic extraction was impossible. In this logically here, we'll see things are not only possible, but we can extract almost all the entropy. Right? So it's in fact, from the land of impossibility, I'm getting to the land of greed. I said I want to extract everything. So the measure of efficiency will be the thing called entropy loss, which is the difference between the entropy of my source and the length of R. Okay? So, and we'll be able to extract from all high entropy distributions. So the availability of this random seed suddenly turns impossibility to possibility. And there is a low bound of Radhakrishnan and Tashma, famous low bound that says that epsilon secure extractor has entropy loss at least 2 times log 1 of epsilon, which is basically 2 times security parameter. Okay. And so here I'm going to give you a summary slide, and then we're going to switch to some different slides about it. So, but here will be basically the next few slides will tell you a summary of what will happen for the next hour, basically for the first hour. So then there is this famous result called leftover hash lemma. It actually says, you know what, we can actually achieve it. We can achieve this optimal entropy loss, something called universal hashing. I'll define it. If you don't know, I'll define it, like 20 slides from now. It achieves this optimal entropy loss. 2 times security parameter. So this is great. So the problems, of course, is, and we've written papers about all of them. So I have like a cool paper of Krzysztof. If in the case, hypothetical case that I'll finish this part before the break, which is not going to happen the way I'm going, I have some slides about the seed length, but I don't think we'll get to it. So I'm going to talk mainly about the entropy loss of leftover hash lemma, and say that even though it looks like great, we match the optimal result, somehow it's not great. So let me talk about this. So how bad is this entropy loss, right? Are we done? Should we be happy with this entropy loss in the seeded case? So unfortunately, many sources in reality, they don't have this extra 2 times security parameter bits. Let's say if the security parameter is 64, and I want to extract 128-bit AES key or something like that, it means that mean entropy of my source has to be like 256. So that's kind of double, right? So it looks like additive, but for practical parameters, it becomes kind of too big. And the point is, like for some applications, let's say Diffie-Hellman key, right? So we get like, we do Diffie-Hellman key exchange, we get a random element in some group. And the group, it's kind of messy enough that even though in principle we should be able to deterministically extract the easiest extractors, well, and some of them I actually do, they just look at the least significant bits, but a very common practice actually to use like probabilistic randomness extraction in this case. And we would like to minimize the entropy loss because if I need to have entropy 256, it means that I need to have a larger group, and that translates to efficiency. So it's actually kind of non-trivial. So a lot of people like really tries to minimize the size of the elliptic curve group. And the other thing that is going against us, if you use like something like HMAC or some kind of SHA or something like that, some cryptographic hash function as your extractor, heuristically, it's very easy to see. I have some calculation maybe. We'll come back to this calculation, but it's very easy to see that cryptographic hash functions in the random oracle models, they have no entropy loss. Basically, they magically convert unpredictability to randomness at the exchange course 1-to-1. So there is no kind of additive loss. And so in result, practitioners actually prefer not to use leftover hash lemma, even though in theory, leftover hash lemma should be faster than SHA-2. But somehow, because of this heuristic and so on, people prefer to use cryptographic hash functions. And we will come back to this point in the second part of this thing. I will give you another reason why you should prefer cryptographic hash functions for extraction. Anyway, so the question is, can we provably improve this entropy loss for KDFs despite the optimality? Okay, so this is the thing that we're going to talk. And this is also, actually, I forgot that. So this is another cartoon. I think this is the last one. So this is my claim of fame. This is the only time, not personally, but something that I'm related to was mentioned in the New Yorker magazine. I guess, again, maybe it's not popular here, but it's a famous magazine in the United States. So there was a crypt. Yeah, so anyways, this is like one of the earliest serious articles about Bitcoin in popular press. And basically, the story is the person came to Crypto 2011 when I presented this paper with Krzysztof about like improved leftover hash lemma and things like that. And basically, the premise, so it wasn't like super complimentary citation of our paper, leftover hash lemma revisited, but basically, the person said, yeah, I thought cryptographers like serious people, but then I come to crypto and I see these funny titles like leftover hash lemma revisited and Merkle puzzles and the quantum world, and I lost all respect for the field or something like that. So anyway, I'll take the reference. So that's the only time we got reference in New Yorker. So what did we do? So essentially, the question we kind of asked in a series of work is, do we need to derive statistically random R, right, for our applications? And for some applications, the answer is yes. If you want to really use one-time pad encryption, it's not hard to see that it's basically if and only if. If you want to have information theoretic security, R has to be statistically secure. But what turns out in a series of work, we show that for many applications, even if you want some kind of information theoretic security in a well-defined sense, we have a series of papers starting with the Crypto 11 paper, but then there was a series of papers at TCC and Eurocrypt about beating this bound. And the key insight is that there is a difference between extraction and key derivation. Okay, so this is what I'm going to show. So this is basically the summary table of our results, and then I'll switch to another set of slides to go a little bit in depth. Okay, so this is what we basically knew before our work, that using leftover hash lemma, we can have entropy loss 2 log 1 over epsilon. So in terms of concrete parameters, if I want to extract AES key with security 2 to the minus 64, for example, I need entropy 256. If I use cryptographic hash functions in the random oracle model, basically I have entropy loss 0. So basically, I can just need 128 bits of entropy. So what can we do in between? So first we define, and I will define what it means, we define a class of cryptographic applications, which includes a lot of applications, for example, symmetrically secure encryption or CCA encryption or whatever, where we showed that the same universal hash function which uses leftover hash lemma, you can halve the entropy loss. You don't need entropy loss 2 log 1 over epsilon, we can only get half of it, and still get basically the same securities. There are no assumptions. And so concretely, it means that we, for example, need 192 bits of entropy for our like Diffie-Hellman key exchange. Then if you're saying, well, this is a pretty general class of application, but it doesn't include everything. It doesn't include like PRFs and a few applications. Anyway, if you want to do a computation, if you throw a little bit of like pseudorandom generator or a little bit cryptography, which we also show is essential, you can basically have this, using cryptography, you can effectively get this extra factor here. So for practical setting of parameters, assuming our PRG is as secure as we want to get our final application, basically we will match this result under computational assumptions. So this will be like a computationally secure key derivations function under like minimal assumptions, like basically using any PRG. I can get essentially entropy loss of this form. So basically it will be almost the same. And finally, at Eurocrypt 2014, another paper, I think, with Krzysztof and Daniel Wicks, we show that, yeah, if you're willing, if you want to do key derivation function for all unpredictability applications, like digital signature scheme or mass authentication, codes and so on. So for example, for Bitcoin, I think cryptography is only used for digital signature scheme, right? That's the only cryptography which is, key cryptography which is used. So in principle, not that I'm recommending you use it for this application, but the entropy loss goes from 2 log 1 of epsilon to basically double logarithmic. It's like log 1 of epsilon, and it's not just up to like constant factors. We figured out exact constants. So for example, you would get like 138 bits of entropy. So almost matching heuristic extractors for this. All right, so let me switch to. So this is basically so what I'm going to do. I'm going to switch to another. I tried to import them here, but because I use different things, everything kind of got messed up. So I'll switch to a different slides. But yeah.
You earlier mentioned this result that secure encryption implies secure extraction, and there, so it's implied computational extraction, right? Extraction with computational security, and that's what you'll also use in the difference with, yeah? Okay,
so there is one confusion, very good point, Chris. Yeah, sorry. So in all these results, I assume the availability, so the result that I showed before I switched to this CD thread to the workarounds, in that result, I just assume there is the only randomness is from our entropy source. Here, I assume there is public randomness. So basically, in this model, I assume there exists a public seed, and so this is a different model. So that's why it overcomes this impossibility result. Yeah, sorry, yeah, that's exactly. It's one of the workarounds. That availability of public randomness helps me to get secret randomness. Good. So basically, when I'm going to go,
sorry.
Question.
Sorry, I didn't catch this earlier, but why is there an asterisk for the input entropy on your 4th row, like 192-bit? Yeah.
What it is? So this is just a concrete.
So why is there an asterisk for your 4th result?
So let me explain you what this column is. Hopefully, I'll answer your question. So this is like basically a concrete example for this application. Where is this? Yeah, here. So I just said, okay, let's say concretely, assume we want to extract 128-bit key with security 2 to the minus 64. What is the input entropy that you want? So this is like a concrete example. So this column is like general. Everything is general except for the last column. So this is general, and the last column is a specific example. So a specific example for epsilon 2 to the minus 64, the length is r, and I'm just telling what is the mean entropy of the input, which will give me what I want. And basically, so in these settings, basically, what we showed is that if you want to build extractors for cryptographic, to derive key for cryptographic applications, you don't necessarily need to do statistically something which is statistically random. So some cryptographic applications form a restricted set of games where you can overcome these impossibility results and get this provable security. Does it make sense?
I think the question was about the asterisk.
Yeah, the star.
Just because I said, okay, oh yeah, sorry, yeah, I'm sorry. It's hard to hear some who's acoustic. Yeah, it's just because, so this is the exact term, and I said assuming epsilon PRG is also 2 to the minus 64. So I just plugged in a specific number, right, because it depends. So this results unconditional, this results use pseudorandom generator, so I said, okay, let's just assume PRG, I don't know, I just put like a concrete security for the, yeah, sorry, good question. All right, so let's switch to the other slide. Sorry that I couldn't import them, everything got messed up, but we'll come back to this thing later, and basically the second half of the thing will be here. So there will be a little bit of repetition. So Jean-Paul, what time should I finish so that I can? Oh, so only 15 minutes. Okay. All right. So I'll give you something then. So we'll go a little bit. No, but you have 45 Oh, 45 minutes. Okay. Oh, I got scared. I was like, oh my, 15 minutes. Okay, 45 minutes. Okay, we'll be fine. Good, good, good. So basically, for the next 45 minutes, I'll talk about this, and then the second half of the lecture, we'll get back to the problem, pseudo-random number generators, and go from theory back to kind of practice. Even though this thing. So anyway, so let me tell you a little bit about, so basically we are zooming in on the tables that I gave you there. So I'll tell you a little bit about how those results are obtained and what is the insight on this randomness extraction. So let's be a little bit more precise. So our setting is the following. So I have some application P. It could be a digital signature or maybe, I don't know, Bitcoin, deriving a key for a Bitcoin or something, which needs an m-bit secret key R. And in theory, I would just pick the key uniformly at random. But in practice, of course, I have some imperfect randomness, some timing of interrupts or something like that, or maybe a Diffie-Hellman key exchange or biometric data or something like that. And I want to convert this X to R. So what we need is exactly what I call a key derivation function before. So in this case, it's, as we'll see, it will be seeded. But here, I'm just kind of cheating. I'm not putting the seed temporarily. So we need like a bridge. We need to convert our n-bit source to m-bit output, which is good for P. And only assuming that X, so as I said, will be a little bit of repetition here, but so we'll just go through it quickly. So, and we'll ask like this kind of, basically this is the main question we'll ask, which is the last column of this entropy loss column. What is the minimal entropy K enough to achieve real security roughly the same as ideal security? Where ideal security will be if my key was truly uniform random, and red will be if I use actually a derived key instead of this. And the dream will be like no entropy loss, right? So this is like the dream. And a dual question, which I will not spend too much time, but it was kind of interesting that we can achieve. We can say it's like the dual thing. Assume I insist on no entropy loss because I want to match cryptographic hash functions. What is the best security I can get with, basically no entropy loss? But for now, let's mainly think about this. And ideally, of course, we can match both of them actually the same. That's what cryptographic hash functions give us. Can we hope to achieve comparable security without entropy loss? Okay, so that's kind of our big goal. So going a little bit, let's formalize this problem. So in the real case, we pick an m-bit key uniformly at random and assume the application P, some who is epsilon secure against a certain class of attackers. I don't really care if the attacker is computationally bounded, whatever, maybe unbounded. So somehow we assume the application is epsilon secure. In the real model, which will be denoted in red, I'm going to derive this derived key. I assume that the only thing I know about my source is that it has entropy K. So this is a definition of mean entropy for those, yeah, implicitly assume it, but this is a formal definition of mean entropy. No strings happen with probability more than 2 to the minus k. And I have this carefully designed key derivation function. And my goal is to prove that the same application P, which was designed to work with truly uniform keys, somehow works pretty well, but maybe has epsilon prime security with derived keys. Okay, so this is the things that we have. And of course, we design the hash function H, but it has to work for any kind of nk source. It has so the same hash function has to work for all high entropy distributions, right? So somehow they have to work in pair, the key and whatever. I guess, yeah, I forgot there are more cartoons, but not too many, not many more. So they kind of have to be in harmony. So anyway, so what is the smallest epsilon prime, right? That's our question. What is the smallest epsilon prime we can achieve? So concretely, the way we'll formalize, this is the main question that we are going to study formally. What is the minimal entropy K? Call it K star, so that epsilon prime, for example, is 2 epsilon, just arbitrarily something kind of reasonably close to the original epsilon. And no entropy loss would be, of course, K star is equal to M. Alternatively, if K is exactly equal to M, what is the smallest epsilon prime, which we call epsilon star? And again, we hope that we can achieve something comparable. And dream 3 will be basically that both can be achieved at the same time or something like that. All right. So now let me tell you precisely. I will not prove it. It's like a 2-line derivation, but it's pretty easy to see that if you use if you look at the key derivation in the random oracle model, this would be a quantitative version of the result. If you look at the random oracle as an extractor, basically, I'm saying epsilon, the new security is original security, plus the probability that the attacker managed to query random oracle on my source X. Because if the random oracle is not queried on exactly the entropy source, and there is no information, so very good. And there is a little bit, it's literally 2 lines, but it's just, trust me, it's very easy to get that. You can kind of translate it into this formula. So if you want, I can try to do it. I might get confused, but it's literally 2 lines. And this formalizes exactly what I said. If you plug m equals k So meaning that the number of bits I extract is my mean entropy, I get 2 epsilon. Right, so this is exactly why this dream 3 is true, that we basically achieve the best of both worlds using this heuristic key derivation in the random oracle model. Okay, so our question is, well, how close can we get with provable security without the random oracle model? Is the question clear? So this is kind of, we are trying to get close to this formula, but provable. So this is like repeated slide, of course, I already talked about. So the way we are going to do it, we are going to have, as I said, deterministic randomness extraction I proved to you is impossible. So we're going to look at the seeded model, and with the availability of the seed, this is just repetition. Good. So, but this is the first time. So this is formally what a Kdelta extractor means. Kdelta extractor, it means that it's this seeded function x. It has a seed such that no distinguisher D can tell apart extracted randomness from true randomness even when given the seed. So the best advantage any even computationally bounded distinguisher can do is this function delta. Right, so this is a definition of extractor, and so this is statistical distance. And a trivial application basically says that if I have a Kdelta extractor, then my epsilon prime is epsilon plus delta. I mean, this is like, because whatever my security game, I can translate it to distinguisher. So basically, there are 2 ways to break the system. You can break it with uniform key, or you can tell apart the key from uniform. So this is kind of trivial. And one thing that will be helpful, I don't want to spend too much time on it, in this, to get these things, the distinguisher is basically whatever our security game for encryption, like I can distinguish encryption of 0 from encryption of 1 or something like that. Basically, a distinguisher will be kind of a combination of the attacker and the challenger in the game. And the distinguisher output 1 if the attacker won the game. So this is our philosophy. So what we are going to try to ask a question is, what is special about a cryptographic application? How special are those distinguishers that there is a combination of, the attacker and the challenger in a particular cryptographic game? Right, so this is going to be basically the question. So now I'll tell you a little bit the parameters of leftover hash lemma. And somewhere as we are going to improve it, you will see the proof of it, but for now I'm just telling you the numbers. So specifically, leftover hash lemma says that universal hash functions, they achieve this, the statistical error delta is square root of 2 to the m minus k. So this is essentially the, so I cannot quite, so in particular, what it shows, it means that for any application P, basically my error epsilon prime is the original error plus the statistical distance of the extractor. So this is what it gives us. So in particular, this is where this 2 log 1 of epsilon comes in. If I set m to be k minus 2 log 1 of epsilon, that's, that's how I get another epsilon, right? So this is basically, why we get this entropy loss 2 log 1 of epsilon. And on the other hand, leftover hash lemmas gives us absolutely nothing. If m is equal to k, I get 1. I mean, basically, I have to lose something. In this level of generality, I have to lose something. I cannot extract everything that I have. And the Radhakrishnan-Tashma bound quantitatively, it actually shows that delta is greater or equal than this. So this is absolutely the best possible, like exactly. So this is the bound. Okay, so this is what we have. I mean, basically translating this table, but with more parameters. So computationally secure guy have entropy loss 0. Leftover hash lemma can give you this. And if you compare the error terms, this is the gap. From epsilon times 2 to the m minus k, we get this thing, which is kind of independent of a cryptographic, So we are going to try to narrow this gap between upper and lower bound. Okay, so any questions so far? Okay, so hopefully it will be clearer when I, so this is like repetition of the previous slide. Let's, okay, so this is how we are going to approach this thing. Basically, we are going to restrict the power of the distinguisher for particular applications. And in particular, where I'm going to start, so we probably will not have time to talk about this. We have some results about this. We are going to argue in the series of papers that cryptographic games actually implicitly restrict the distinguisher in a way that we don't need to follow this Radhakrishnan-Tashma bound, that we can do actually better for cryptographic games. And this is like a related thing. So those are dual questions. There will be the same observation looked from 2 different things. Good. So let me, so this is the same punchline I put on the previous slide. In fact, I actually copied it from these slides to the other one. That there is a difference between extraction and key derivation. Key derivation is a more restricted problem than extraction. Okay, so let me tell you essentially a canonical example which will be the easiest to understand. Assume I want to derive a key for, let's say, a digital signature scheme. Right? I want to, compute, or maybe for a Mac or something like that. So in this game, the advantage of the attacker in my game, which is a probability that he wins the game, is probability that some event happens. So I forged a signature, right? So there is some event, and so the way I define my advantage is a probability that something happens. And by loss of probability, this is a number between 0 and 1. That's the only thing I need to know for this, for improving leftover hash lemma, as we will see, for this set of applications. So the advantage of the attacker is a number between 0 and 1. So let's look at the, let's say, key derivation for signature and Mac. So assume we know that the probability whatever particular attacker forges a signature with uniform key is at most epsilon. Okay? I want to get that the probability the attacker forges the thing with extracted key is epsilon prime. Right? This is what I want. And the key inside is, in this case, we never care. If you look at this distinguisher almost never outputs 1. Right? Because if it outputs 1, it means that a scheme was insecure to begin with. Right? So basically, I only care about distinguishers who almost never output 1. Right? They almost always output 0. Because otherwise, our scheme is insecure. So basically, this probability is very small. And as you will see, we can get better key derivation functions if we restrict for these distinguishers. For example, just to give you an example, instead of additive error, in this case, it's OK to have a multiplicative error. Right? Let's say if I talk about encryption scheme and I say, OK, the attacker breaks encryption scheme, it's probably at most like 50 plus negligible or something like that for encryption scheme. The factor of 2 would be horrible, right? Right? From 1/2 times 2 is 1. So it's like from probability 50%, the attacker wins, breaks encryption with probability 1. It's horrible. For signature scheme, if it breaks this probability, 2 to the minus 59, and now we are 2 to the minus 58, is not too bad. Right? So for this kind of application, for example, a multiplicative loss is OK. So basically, we have more room to maneuver in some sense. Right? So, and this leads us to this notion of unpredictability extractors. So unpredictability extractor will say that unpredictability extractor, it's k epsilon epsilon prime unpredictability extractor if the following is true. If my distinguisher on uniform key outputs 1 with probability epsilon, then it will output 1 on the output of the extractor with probability at most epsilon prime. Right? So this is kind of, rather than insisting on this additive distance between epsilon to epsilon plus delta, I'm just making it 2 parameters, epsilon and epsilon prime. And this is a theorem that we proved in Eurocrypt 14 in this paper with Daniel and Krzysztof. There are several parameters. This is like the interesting one. I don't know if you can see it. This color is, I can barely see it. I'm looking with the glasses, but I know the results, so hopefully I'll tell you correctly. Yeah. K, good. So yeah, good. K is the mean entropy of X. So remember, so throughout this slide, K will be the entropy of our source, and I want to go from K bits to a little bit less, and I'm looking at the entropy loss. How much less than K bits can I extract? So yeah, K is the entropy of my source, and so here I'm saying, as long as the distinguisher almost never outputs 1, I want the same distinguisher almost never output 1 on extracted key. And for example, here, surprisingly, we show that we can achieve, let's say, epsilon prime. OK, not 2, OK, we achieved 3, just so that the numbers are nice. We can achieve epsilon prime 3 epsilon, and the entropy loss is only log 1 of epsilon. So instead of 2 log 1 of epsilon, we get log 1 of epsilon plus 4 if you want, because I promised you to get no hidden kind of constants. There is another regime for k equals m. Remember, but let's ignore. For k epsilon m, we can go a little bit worse. So if you want to have no entropy loss, we can still get like epsilon times something small. But let's concentrate on this one. So, so this is a plan of attack, and I'll keep it kind of high level. So this is our plan of attack. Why this would be possible, right? So you can already see. So this already overcomes the Radhakrishnan and Tashma law bounds in a pretty big generality, right? So essentially, the point is for encryption application, unfortunately, it doesn't completely apply because there we care about attackers between like 49 and 51%, which is unfortunately multiplied by 2 doesn't give us anything. But for signature schemes, we are good, right? We can cover these things. So this will be our plan of attack. So the plan of attack is basically the following. To design those unpredictability extractors, we do it in 2 steps. Okay? So the first step will be, it's a generic observation of independent interest. It says that for any applications, for any unpredictability applications, those applications already work pretty well if the key have almost full entropy. Right? So for example, let's say I'm using a key for a MAC or a signature scheme. Right? Normally I'm supposed, let's say, to use like for CBC MAC or something like that, I'm supposed to pick 128 bits uniformly at random. Let's say I fix the first bit to 0 and the other 127 bits are uniformly at random. Right? For something like one-time pad is a disaster. Like the first bit of the message is like, well, it's known, right? Because you know that the one-time pad is 0. For a Mac, I claim, if you think about it, and I will give you a proof in the next slide, I claim that, yeah, I can lose security, but I can lose at most a factor of 2 in security, right? Because essentially, even a truly random key will have the first bit 0 with probability a half, so it's like a simple derivation that basically it's not catastrophic, right? So this is the first thing. So let's actually do this step 1 formally. It will be like pretty simple. So fix application P in any legal attacker F. Let's define this function f of r, the advantage of our attacker on a particular secret key. So on a particular derived key R, the attacker, for some keys, the attacker can have better advantage than for the other keys, like there are weak keys for all kinds of schemes. Let's measure it as a function f of r. And the ideal security, we can actually mathematically express it as the expected value f on the uniform distribution. Because the ideal key is truly uniform. So on average, the advantage of the attacker is exactly the expectation of this function f on the uniform distribution. So this is essentially what our epsilon is, right? The security of epsilon is expected value of f of r. Real advantage is expected value of f of r, where r is our derived key. It's like hash of whatever, hash of x or something like that. So it has some probability distribution. I know what it is, but this is the answer. And the simple lemma says that if my R has mean entropy almost full, it has only, this is called entropy deficiency. Let's say if it has entropy m minus 1, expected value of f of r is at most 2 to the d. So there is this exponential degradation. Every bit of entropy deficiency kind of causes exponentially, but if it's a constant or it's a small number, it's not too bad. If the number is 1 or 2, it's not horrible, right? And the proof is like one line, right? So what is this? It's at most 2 to the m times this maximum, right? And this maximum is exactly 2 to the m minus d, which is one line proof, right? So this is like a formal thing that if the key is almost full entropy, it matches up perfectly with the, right? So I kind of tried to condense it to one line, but hopefully you can see there is nothing deep going on here. Good. So the corollary, in particular, is that as long as the mean entropy of the derived key is m minus d, epsilon prime is at most 2 to the epsilon times this. Right? So yeah, I think we're doing well on time, so I'll not rush too much. So this is basically the end of step 1. Says, you know what? All we need to argue is that our derived key is high entropy. As long as we ensure that our derived key after the key derivation function has almost full entropy, it doesn't have to be statistically random. So basically, this is my point. My point is, from predictability application, I don't need to derive keys which are statistically random. I need to derive keys which are almost full entropy, right? Just m minus 1 or something like that. And now, and this primitive is actually in complexity theory, it's called a condenser as opposed to extractor. So it starts with something which has entropy scattered around, and you kind of compresses it. Maybe it's not completely random, but you compresses it to this kind of high entropy distribution. So, and I'll define it on the next slide. But in this regime, this is what our theorem looks like in the language of condensers. Basically, we can achieve extremely low D. For example, for entropy loss 1, this is what we achieve. We achieve a key whose mean entropy is m minus 1, provided that the entropy of the source is only like this m plus log log. So this is essentially our kind of observation. That for condensers, so for those who kind of know a little bit of complexity theory, it's for condensers, the entropy loss doesn't need to be 2 log 1 of epsilon, it's only log log. That's basically a translation of our thing in the language of condensers. And let me see if I want to go. So yeah, it's like I realize there are more letters that I wanted here. But anyway, I'll just give you the definition of condenser and maybe just a high level how we prove it, and then we move to a different application. So Anyway, KD epsilon condenser has a property that the output distribution is statistically close to some source ys, where y has entropy at least m minus d condition on the seed. So this is like in the seeded regime, this is what the definition of condenser is. So KD epsilon condenser has this property that the output distribution, maybe it's not, I cannot kind of guarantee that the output distribution always has mean entropy, but it's statistically close to something that has mean entropy. And that's kind of good enough for our applications. So once I do this kind of thing, if you look at this kind of definition, what it shows you in this language, that my final security epsilon prime is the original security plus 2 to the d times epsilon. So basically in this language, this is where I got 3. Remember I got 3 epsilon. This is 1 plus 2 to the 1, right? Remember, anyway. This is why we got 3 and not 2. So just a philosophical point is extractors achieve d equals 0, right? Extractor says that the output of the extractor is epsilon close to a distribution which has entropy deficiency 0, which is the only distribution with entropy deficiency 0 is a uniform distribution. And here we are saying, so extractors have entropy deficiency 0, but Radhakrishnan-Tashma bound says you have to have this entropy loss. And our theorem basically says that just if I'm willing to have entropy loss 1, or entropy deficiency 1, suddenly the entropy loss goes from 2 log 1 of epsilon to log log, basically. Let's skip option 2. So maybe I'll skip the proof. So somehow it's getting more technical than I wanted. I promised a high-level thing. But basically, let me see. Do I want to give you the idea of the proof, or we just... yeah, maybe let's give the proof. It's not very hard, but it's a pretty simple calculation. So it's not super technical, but basically, it's basically a simple question about balls and bins. So imagine that, so my goal is to, I have this distribution, it has various weights, and I want to throw it at random I want to extract. So the way I will do it is basically to throw these things into kind of random bins. And the observation is mean entropy corresponds to the largest bin. And it's pretty easy to see that if I'm willing to have a multiplicative factor away from the uniform distribution, things are kind of good. So let me skip this thing. Sorry, I'll just summarize this thing. So because I don't want to get too technical unless you guys want me to. But it's just basically once we get this observation, the rest is just calculation. There is nothing super deep going on. We need to flex our muscles, but the insight is that condenser is enough to get keys for signature schemes. So let me tell you the maybe more surprising things. So
Yevgeniy,
yeah.
So how do you build a condenser?
Yeah, so in this particular thing, what we show, this is actually, I'll show it here. So it turns out that unfortunately, pairwise independent hash is not a good condenser, or it has pretty poor condensing properties, unfortunately, which will not translate to a good bound. So what we showed is, so one thing which is easy to see that a random function is a good condenser, but that's huge seed. A random function means that the seed is the whole description of the function. What we showed is, and this is what is balls and bins. Basically, we said, assume my condenser will be a random function. It has a huge seed length, but let's ignore it for now. Then basically, we get the parameters of our theorem. And the next observation was I don't need a full wise independence. So it turns out that this is the punchline that I just need to have this log 1 of epsilon wise independent hash function. So like a polynomial or something like that. So it's not pairwise independent like universal hash function. But yeah, so basically, the concrete function was, so this is theoretical result. I think it's cool that, but yeah, it's so this will be 64 wise independent hash function, right? So my condenser in this case, will not be more efficient than Shine practice, but yeah, if I have a 64 wise independent hash function, that will give me this entropy loss 10. But now it's provably secure. I don't need to rely on the random oracle model. But basically the operation is you do the analysis with truly random thing, and then you notice that you don't need for the particular kind of Chernow bounds that you need. Yeah, Chernow bound works, but it turns out we don't need Chernow bounds. We can do this weaker bound, and this turns out to be, so it's heavy, it's very technical calculation, but nothing deep is going on. It's just kind of, grinding some Chernow whatever bounds. So, but yeah, very good question. Yeah, so so this is not super efficient, but it's not horrible, right? 64 ways independent hash functions you can conceivably build, so it's not practical. I'm not going to suggest to do it in the RNG thing, and the RNG will go a different route, but anyway. So as I said, this kind of tutorial I start with theory, and as we go to the end, we'll end up in practice, hopefully something that Linux is going to use. But yeah, so we start with theory and end up with practice. So this would be our particular examples, kind of translated here. I mean, ignore this epsilon star. This would be just essentially heuristic key derivation says I just need 128 bits of random entropy. Leftover hash lemma says if I need a key for CBC MAC, you know, I need to get 256 bits of entropy, and our result, you know, will say that I need only 138 bits of entropy. So, so it's pretty good. Good. So let me tell you the second thing. So this is, I think, arguably the most surprising thing. So when we discovered that, I think I was really surprised. So maybe unpredictability was a more technical calculation, but this one to me was the most surprising thing. So let me tell you the second thing, which will be maybe the last thing before the break. Good. So how do we deal with indistinguishability applications, right? So first of all, we should know that we are not going to succeed for all of them. Because as I told you, for one-time pad, I need a statistically random R. There is nothing I can do. So how do I restrict to the class of indistinguishability applications where I can get better entropy loss? Well, all right, let's have a plan of attack, and then we'll see what we get out of it. So we're going to identify a subclass of indistinguishability applications, which, just like for signature schemes, we figured out that the like any signature schemes, the only thing it needs is a high entropy key. The key should be almost uniform, like it should have small entropy deficiencies. So here there will be a different property, but we will still try to identify the property of you know, this class of applications, which always work well on high entropy key. And on a technical level, I'll define it on the next slide. It turns out there is a more convenient notion of entropy for this application, and you will see exactly why on the next slide. Something called Renyi entropy. So we'll get the weaker inequalities than we get for unpredictability applications, but we'll still beat the leftover hash lemma. So that's kind of going to be a punchline. And so we will still, so essentially at the end, it will be very similar structure. We identify the class of applications which works with high entropy key. We will still need condenser, but instead of mean entropy, we'll need a condenser for this Renyi entropy, which will have weaker parameters, but we'll still succeed, basically. So this is the point. The condensers are the right thing to work in this kind of thing. So let me tell you this application. This is like, I think this is a cool thing. So that was somewhat surprising. And in parallel, if you haven't seen the proof of leftover hash lemma, I'll give you a proof of leftover hash lemma as a bonus. It will be a special case of what I'm going to show you. So first, I want to define the Renyi entropy, which is also the collision probability. It means that if you take two samples, independent samples of the distribution, what is the probability they collide? Right? So this is like expressible as the sum of P of R square. And it's easy to see that this is a low bound. So mean entropy is more conservative notion of entropy. So any distribution has less mean entropy than it has collision entropy. And this is a key lemma. It's surprising. It's like a 3-line lemma. It looks maybe more difficult, but this is all we need to basically get our improvement to leftover hash lemma. So remember, this is essentially the advantage of the attacker on uniform key. And this is the advantage of the attacker on a derived key. Intuitive. Remember, this was like our function R. And what we are saying is for any function f, now it doesn't have to be between 0 and 1. It could have anything, or it doesn't have to be like small or whatever. So for any function f, this is essentially what we are saying, that as long as R has almost full entropy, basically the difference is, yes, there is a still exponential factor 2 to the d minus 1, but here there is this very weird thing. It's hard to read, but this is expectation of f squared. So this is the inequalities that we are going to get. And the proof, I'll write the first line, and I'll run out of space, but there are only 2 lines. I'll just give you the first line, but you will see how the second line is derived. It's very simple. So what is the left-hand side? Basically, this is P of R times f of R. This is 1 over 2 to the m times f of R. So just do it like that. So when you have something like summation of AI times BI, there is like one thing that you always do. If you're a mathematician, you apply Cauchy-Schwarz. There is nothing else. I mean, if you're a fancy mathematician, you apply Hölder inequality, but we're not fancy. We're just going to use Cauchy-Schwarz. So this is the only thing we can do. So it's just, you know, so we apply it, we get these 2 terms. This term is exactly what I promised. So this is already done. And this term, you kind of expect parameters. You get summation of p squared. Summation of p squared is exactly this mean entropy. So you just massage it around, and you get exactly what I say. So it's like, that's it. It's, I'm skipping the second line, but nothing deep is going on. So basically, the philosophy is here. If the key is almost uniform, you get still exponential loss, but there is this second term which is a little bit weird. So we'll have to understand this second term in some sense. So any questions so far? Great. So this is basically the proof of this lemma. So yeah, I'm repeating it here. So why is it nice? First of all, I no longer need f to be like positive or whatever. I can have 1/2. There is like no restrictions on this thing. So it's okay even for indistinguishability applications. So it's true for any applications. And then we achieve this kind of separation of powers. The first term, it's only the function of the mean entropy of R. Right? So it's just basically the condenser doesn't need to know about the application. So it's just a question of entropy deficiency. And the second application is, right, and the second term is for uniform distribution. So we kind of separate it to achieve the separation. The first thing is a property of our condenser or extractor or whatever, key derivation function. And the second is a property of our application on uniform keys. Right, so you'll be able to understand those things separately, which is good. And I mean, this is like minor, it turns out, yeah, anyway, let's ignore this. So the questions that we should ask now, this question will be some technical things that we will get to that will not be very hard. But the thing that is weird is what is the meaning? So we know that expected value of f, that's basically, we have a name for it, that's security of our application. Right, so basically the probability for indistinguishability applications, the probability the attacker wins the game minus 1/2. So it's a number like between minus 1/2 and 1/2 or something like that. And by definition, it's expected value on uniform keys epsilon. That's how we define epsilon. But what is this term, right? It's like it's a new term. We need to interpret it from the perspective of security, right? That's like a weird term, right? It's the advantage of the square advantage. So that's why it's called square security. So this is, for those you know, it's a very famous painting of Malevich. It's called Black Square. So it just shows that you have to come early. So I wish I invented it and became rich and famous. Even I can draw it, but nobody will pay me for this. But anyway, and this is also not, I use PowerPoint, I cheated. It's not even the original. I just drew my own reproduction of this painting. Anyway, so square security. So we'll say that application is sigma square secure against some class of attackers if any attacker in this class expected value of its advantage square is at most sigma, right? Because that's kind of what I want to get my thing. And the simple lemma which follows from the previous slide, from this lemma, that if P is epsilon secure and sigma square secure, then P is also epsilon secure in this M minus D real model. So M minus D real model means if the key has entropy deficiency M minus D, where epsilon is like the original security plus this term that I, right? So that's exactly, this is how delta was defined on the square root, and this was this square root of 2 to the D minus 1, right? So this is like a generic lemma. So all we need is to figure out what are the square secure applications, right? And what does it even mean? It's like some really bizarre thing. So it motivates studying square security. And in particular, what we're going to do, because nobody designs those square secure applications, we will see that some applications like chosen plain secure encryption, they were defined in terms of regular security, but we can relate square security of these applications to their regular security. So that's like a surprising application. So once we relate it generically, we kind of get those generic implications. Okay. So any questions so far, about this? Yeah.
Maybe. So before you showed that encryption implies extraction.
Yeah.
So does this contradict that a bit, or?
Well, it does. In a sense, it's a seeded model. Yeah. So all those things. So I apologize. Yeah. In all those things, the extractor, if you look even, well, I mean. Like, for example, even if I go back to the signature application, it doesn't contradict it because, for example, when you go to signature, there is a seed-s, right? So all those things are in the seeded model. So the seeded model overcomes impossibility of extraction. So yes, that impossibility of extraction is, well, first of all, it doesn't contradict it because, so the short answer is yeah, it doesn't contradict it, but all these applications are seeded. There is like an extra seed, so we don't have to worry about possibility of extraction. But anyway, what we show, we don't even need extraction. We just need condensing. But yeah, it doesn't contradict.
Okay, so that previous result, the one in the beginning, that
the one that I showed before.
Encryption
the one that
implies,
showed before.
What is the main takeaway of that one?
Yeah, so that result was stronger in some sense. That result that I showed before at the beginning, it shows that if you have encryption that works for some family of sources, then you have a deterministic extractor. So basically, encryption implies deterministic extraction, right? Here I'm studying probabilistic extraction and not even extraction, even condensing. So this is like the best way to say it's like one avenue to overcome the impossibility result is through this seed. But I think it doesn't contradict it, right? That result shows that you even have deterministic extraction. Here, well, sure. I mean, but because I want some very good parameters, I'm building, probabilistic kind of extraction. But yeah, it doesn't contradict as a kind of, I think, complementary. But yeah, it's. So to come back here, just to get to the punchline, I think we are very close. Yeah.
So if you go to your current slide,
This, back or forward?
The current slide where you stopped.
Maybe.
On square security. So somehow the question of how square security relates to regular security, maybe I could be wrong, but it seems like if you take the advantage like f of u as a random variable, then this looks like a variance and.
Exactly. So it will be very similar. So you're already stealing the results on the first bullet of the next slide. But yeah, so I'm going to answer this question, and I think you're right. So good. So I think I will answer it on this question. So you already can see that there is some relation, right? It's f squared versus f and so on. So we can use like variance and so on. But for example, here is a very, so I will say that the application is square friendly if sigma is at most epsilon. Right? If it's square security is always guaranteed to be at most its regular security. Right? That will be a definition of a square. Remember on this slide like an hour ago, I had this class of square friendly application. So this is what it means to be square friendly. It's application with sigma. And here's an example of square friendly application. All unpredictability applications are square friendly. Why? Well, the function f, in this case, it's like probability that something happens. It's a number between 0 and 1. If you square a number between 0 and 1, it gets only smaller, right? Square of a number between 0 and 1 is like smaller. So extraction of f squared is at most extraction of f, so sigma is at most epsilon. I mean, we can apply it here, but of course our unpredictability extractors achieve better parameters, only low whatever stuff, but you can get something already here. Right? So this is one very broad class. So all unpredictability applications are square friendly. Well, what about privacy application? So there are still some non-square friendly applications like one-time pet, PRFs, and so on. In the interest of time, I will go, but this is a surprising thing. So this was a really surprising result that we observed. At least to me, it's still surprising. I still have to look up this result. But actually, we show that there are many natural indistinguishability applications like CCPA and CCA encryption, weak pseudo-random functions, QoS independent hash functions, and so on. So you said I have to finish in 15. I think I can show this slide. Yeah, so I have like a backup slide. If you, I can either move forward and we believe it, or I can spend like 2 minutes just to give you an example why chosen plaintext secure application is square friendly. Yeah.
Yes, I would like to particularly the difference between weak PRFs and PRFs.
Exactly. Yeah, the weak PRFs are also square friendly for very similar reasons. So maybe I'll show you this slide, and if we don't finish, it's like that's the main thing that I want to show for this part of the talk. So let's go here just to see this. So this is an example why CPA chosen plaintext one-time pair is like one-time secure encryption. It's not square friendly, but chosen plaintext is square secure encryption will be square friendly. So remember, this is our game for chosen plaintext secure encryption, right? So in here, by the way, I mean, I only care about now the key derivation. It's okay for this application. There is local randomness for encryption. It doesn't bother me, and so on. But anyway, this is a standard game. I choose a secret key R for my key, for let's say it's a symmetric key encryption. So Alice and Bob choose a shared key. So anyway, this is a challenger and this is the attacker. The attacker says, give me encryption of a message M1. I encrypt message M1. Says, give me encryption of some other message, blah, blah, blah. And at the end, after Q messages, you get encryption of arbitrary many messages. I mean, this is not the most general game, but this is good enough for you to see the point, right? Then the attacker says, okay, I claim that I can distinguish encryption of M0 from encryption of M1. You choose a random bit, and you send the ciphertext over here, and the attacker tries to guess, right? So this is this application. So what is the advantage of the attacker? The way we define it is a probability B equals B prime minus a half. That's how, so that if you take the expected value of absolute value of this f, that's how security of encryption is defined, right? It's like, so this kind of thing. So this is my function f of r. For every particular secret key r, we can define this function f of r. So in particular, we can define TQ epsilon security. Q is the number of encryption queries. I want to be quantitative. You will see why I want to be precise about the number of Q. And you can also define, just because I define this function f, you can also define square security. Okay? So this is a key lemma. So the key lemma is that if the encryption is secure against attackers who run in time 2t and make 2q encryption queries, that's how we define. So technically it's like q minus 1, but anyway, this is a game. And it's 2 epsilon secure, then it is tq epsilon square secure. So effectively, if you ignore this factor of 2, sigma is, it's not at most epsilon, but it's at most 2 epsilon, and the resources of the attacker are halved. But basically, if I want to prove tq epsilon square security, I just need to prove slightly, kind of weaker regular security. So this is the lemma, right? So basically, if you see if this lemma is proven, this is qualitatively what I want, right? That regular security. So let me give you the proof. It embarrassingly will fit into one slide. It's like a very simple observation, but yeah, it's a little bit counterintuitive. Okay, so this is observation. So this is the insight. It's like one slide, but it's a little bit tricky. So let's do this one slide, and then we'll go for lunch. Or I will tell you the summary. Sorry. But basically, the insight is that for any attacker A making Q encryption queries, there exists an attacker B who is making 2Q encryption queries. That's why for one-time security, I would need 2-time security, so it kind of doesn't work. Like 1 pair is really 1. I cannot multiply it by 2. But where the advantage of this regular advantage of this attacker is effectively square of the advantage of our original attacker, right? So I want to bound the expected value of, advantage of A square. And basically, I build an attacker B who makes a little bit more encryption queries, whose advantage is exactly what I want to bound, right? So this is kind of the tricky thing, right? So here is B. I'll tell you what this B is, and then we'll see like a one-line derivation why this thing holds, right? So this is my attacker B, right? So first you run A against simulated challenger C. You choose, so and in this case, what do you mean simulating challenger B? It's like I pretend to be the challenger of the attacker. Whenever attacker asks me encryption query, I ask my own challenger encryption query, I forward it to the attacker, but I choose my own selection bit B, and I see if the attacker won the game. Right? So I choose my own bit B and say, oh, did the attacker distinguish 0 from 1 or not? So I run the attacker once and I see if he won the game. Right? And I spend, obviously to simulate the attacker, I need to ask my challenger this. So I spend this budget of Q. So this budget of Q also includes the challenge query. So that's why it was Q minus 1 and 1. Now I run A for real, and now I run it against my own challenger. So now when the attacker gets encryption of M0 from M1, I'll ask my own challenger. And then the attacker will give me the bit B. And the question is, should I believe the attacker or not? And there is a very good strategy for me to believe him or not. It's like, well, if the attacker won the first game, it's probably a good attacker, so I'll believe it. If the attacker lost my own game, I'm going to flip it. Right? So basically, I just test myself, the attacker, pretending to be the challenger. I say, okay, is it a good attacker or is it like this attacker full of nonsense? Okay, so so this is kind of natural, right? So I kind of correct it. If the attacker first time succeeded, so the intuition is normally the way advantage is defined is like probability minus a half. So it could be a number positive and negative, but I claim that with this step, with this self-correction step, will ensure that the advantage of B is always non-negative. So let's see that last derivation. It's literally one line. What is the probability that V wins the game? Basically, B wins the game under the following two conditions. Either I won twice, because in this case I didn't reverse the bit, or A lost twice. Okay, and depending on plus minus versus minus plus, effectively probability is whatever this thing is. I don't know whether it's plus minus, but I know it will be reversed the second time. Basically, it's something square plus the complement of this number square, and if you do this thing, this plus minus cancels out, and you get 1/2 plus 2 epsilon square. So basically, the probability that I win the game is always greater than 1/2 by exactly this function epsilon square. And what it does, so if I come back to this slide, if you look at what is sigma? Sigma is expected of advantage A square, but advantage of A is exactly half advantage of B. That's what I built, right? So it's at most half advantage of B, and the advantage of B was 2 epsilon, right? That's how I. So sorry, how do I know that advantage of B is at most 2 epsilon? That's my assumption. Sorry, right? So because my assumption was that my CPA scheme is 2 epsilon secure against regular attackers who make 2Q queries. This is like an attacker B. That's the attacker B. It makes 2Q queries. Therefore, its advantage is 2 epsilon. So I get my I get my derivation. maybe it comes out of the blue, so I'll pause here. Sorry, we are like almost done with what I wanted to say. Sorry if I'll take an extra minute. But basically, so this is kind of a non-standard, a little bit of a tricky kind of thing, how to get it. So the corollary is, so this is what I want to say, the corollary, that if the encryption scheme is 2T, 2Q, 2 epsilon secure in the normal sense, then it is, so now I'm like applying everything, the whole framework, then basically it will be TQ, and then there is this kind of square root of epsilon times 2 to the D security in this with weak keys. So this is like a generic derivation for, so yes, there is a little bit of a degradation in the runtime and things like that, but this is a generic thing. So anyway, let me skip this, and I just want to come back to conclude this part of the thing before we go for lunch. Sorry about being a little bit more relaxed. So basically coming back to this thing, I'll just put like a summary slide here. So this was a surprising thing, that there are many square-friendly applications which are privacy. So let me, okay, so I will not have time for this, so I'll just tell you what the result is. So this is, so basically what we are showing here, yeah, so what we show here is that universal hash functions, they're good, yeah, they're good. So all it shows that we just need to build this good condenser, but for any entropy. Remember, because for this result we need, this notion of whatever, this any entropy. So maybe I'll, yeah, sorry about it. I mean, if you want, we can start. I can spend the first 5 minutes of this thing. So I'll tell you the punchline. If you guys want me to revisit it after lunch, as opposed to switch gears, I can. So basically, the upshot of this observation is that all we need to do for our key derivation function is to build these condensers for any entropy, for this collision entropy. And this is a very, very simple derivation. So this is, in the new language, the version of leftover hash lemma. It says that universal hash functions are KD epsilon condensers, where D satisfies essentially 2 to the D minus 1 is exactly what I want in the leftover hash lemma. It's 2 to the m minus k. So this is basically the one-line derivation that tells us everything we need to know. Because I'm saying, listen, I choose this universal hash function at random. Now I need to say, I assume I sample the source x twice independently, and I see what is the chance that my derived keys collide. What is the chance? Right? That's how Renyi entropy is defined. So the Renyi entropy of my defined key is the probability that h of x equals h of x prime for 2 independent samples from my entropy source. Well, there are 2 ways they could collide. Either x is equal to x prime, but that has at most 2 to the minus k probability. Maybe let me. Right, so that has 2 to the minus k chance. That's the definition of, either collision entropy or mean entropy, doesn't matter, it will imply here. Or x is not equal to x prime, but the hash collided. And this is exactly the definition of universal hash function. Universal hash function has this property that for any non-equal inputs, if you choose a hash function at random, it's very unlikely to collide. You get this, and if you remember, I mean, I know I'm like throwing, but this is kind of what I want. I want this entropy deficiency D, so it means that I want this number to be less than 2 to the D minus m, and this is the same as this inequality. Anyway, so this is like where I stop here. So basically the corollary is that if P is epsilon secure and square friendly, then universal hash function gives us this key derivation function whose security is original epsilon plus square root of, basically this number. But there is this epsilon is delta, this is a square security times this thing. So anyway, so this is like the slide where I'll stop. Basically, if you remember, leftover hash lemma gave us this, which corresponds to epsilon equals 1. Epsilon is at most 1. But for square-friendly applications, I know that I can actually put, instead of sigma, I can put epsilon, and I get this bound, and I get this line. So sorry if I rushed it a little bit. So yeah, I'll take questions before we, yeah.
Only one.
Yeah. Sorry about it.
So my question is about that square root, because there is like a loss of square root of epsilon, and it seems like here, at least with the same approach, it's inevitable, because if you go back to the slide that you defined like square security, right here. The thing is like larger than epsilon square, like with Jensen's inequality, I guess. So I was wondering if it's like possible to do something else to like not have that square root.
Yeah, so unfortunately, no, that's one of the things that I wasn't going, like 5 slides from now, which I'm not going to. We actually show that these optimal parameters. This entropy loss log 1 of epsilon, we cannot, in this level of generality, we even have some counterexample, some artificial application. So this is tight, yeah, we cannot, I mean, to me, I concentrate on the positive. It's great that we have the entropy loss, but this is tight, yeah, we cannot. Also, this log 1 of epsilon from predictability applications also tight. So all those results have actually, in this level of generality, happen to be optimal. But yeah, it's a good point. It seems like we try to do Hölder inequality and other things, and at some point we just said, okay, let's prove optimality, and we said, okay, it's optimal, so no need to try, unfortunately.
Okay, thanks.